Hey everyone, good morning. Welcome to day two of this great conference. So we are going to be talking today, my session about how do we actually build robust machine learning models, or in other words, successful machine learning models. So I'm Natesh. I'm currently a lead data scientist at Finicity, which is a Mastercard company. So to introduce and motivate today's discussion, let's talk a little bit about why is AI important to us. For this fun exercise, I thought of noting down my daily interactions with AI. And it starts right with, say, for example, Alexa. Like Alexa is the one that actually wakes me up. Right from there to the Apple's Face ID, Facebook's newsfeed, Netflix recommendation system, Reddit, Gmail, and so on. So all of us in our pockets carry a lot of AI today. And one of my favorite applications of AI is actually in self-driving, where AI is actually today driving self-driving cars with less than 5% error rate, which is awesome. But although everyone knows about the power of AI, AI also comes with its own share of failures. For example, on the top left, we have this infamous tweet from Steve Wozniak, Apple's co-founder, when he applied for an Apple card and actually got a credit limit 10 times that of his wife. Although both of them had joint assets, the algorithm basically gave a 10x credit limit to Steve, which, what do you all think? Do you think it's fair? Any takers here? What do you think happened here? So it's a clear case of gender bias, right? And like these are some things that we need to be really watchful for when we are actually building machine learning models, which could I mean in this case a huge reputational risk, right? And actually erodes trust in this particular application. The other uh, the other failure was researchers actually found racial bias in a hospital algorithm, where white patients and black patients had unequal distributions of necessity of hospital beds, which meant that the care wasn't being given to the people who needed them. The bottom left, again, many of you might have seen this, is a problem with Google Translate, where when we are translating language from words from one language to other, the occupations were actually reversed, and you did a reverse translation, which again leads to bias in the training data sets that we actually expose to our models. On the right side, we actually have a bias shown in a face detection algorithm, and these are uh, the state-of-the-art face detection algorithms, built and used by like very big companies, for example, like Microsoft and IBM, which actually found racial bias in the algorithms, which again does not bode well because facial recognition today is also becoming mainstream and being used in say airports, etc. And you definitely don't want to see this kind of a bias in the algorithm. So, I mean, modeling has been around for a while, right? It's been like probably 50, 60 years since statistical models have been around. Why do we need to talk about AI models? Why are they different? I chose to compare them across 5 different dimensions. The first one is data sets. Statistical models are typically small structured data, your beautiful data sets, whereas MLAI typically come with large unstructured data. It can be text, images, videos, and so on. The next one is modeling assumptions. Statistical models have assumptions which we need to cater to. We need to build robust models which actually need to cater to those assumptions. And MLAI models, on the other hand, come with very limited set of assumptions, or if at all. The third one is actually feature engineering, where for statistical models, we actually need to do extensive feature engineering. We need to do a lot of handcrafting, etc. Whereas MLAI models actually do the feature engineering heavy lifting for us. A lot of times, the AI models themselves are the feature extractors. The next one is model complexity. So as we all know, like model complexity for statistical models is super low, whereas for MLA models, it can tend to be very complex. A few of you might be aware that Google launched a model called Palm, like I think it's been 10 days now, which has 540 billion parameters. I don't even know how many zeros are in that number. And the last dimension is actually model interpretability, where for statistical models, it's very high. For example, for a regression model, we actually have the model coefficients, which actually tell us what the effect of a change in a feature would actually be on the target variable. Whereas for MLA models, interpretability is low as we speak. I put an asterisk there because I do want to allude to the great research that's been happening on explainability and interpretability of complicated models as well, which I think is a great step in helping us unlock the true power of MLA models, because a lot of industries, interpretability and explainability are actually bottlenecks to mass adoption, because we need to be able to explain to our clients, customers, why we actually took a particular decision. So with that context being set, I would like to talk a little bit about um, an ML modeling pipeline, in my view, which actually caters to a different facets of actually building a successful and a robust machine learning model. The first step is that of pre-modeling, where we actually need to think about why are we even building this model. We need to think about the business rationale. We need to get alignment with business users. We need to, the next step is once hopefully, everybody is on the same page as to why we are doing this, we have the budget, the resources, etc. We actually need to think about data. This is something that, can be very challenging depending on the organization. Like to even get like a good consistent source of data is a challenge. And once we cross these hurdles, then we need to come to the what features are we using? Are we using the right set of features? Then we actually need to have like a good set of features to be used into the model. And the next piece is actually the modeling phase, where we need to decide the model algorithm, do some hyperparameter tuning, analyze the model performance, and do some benchmarking if especially we are replacing a legacy model. In some cases, we might have to benchmark with an external model just to give us confidence to our stakeholders. And the last step is actually the model usage, which is like, hey, we have a model, we have an endpoint ready, but then we actually need to think about interpretability. Hey, does the model need to be interpretable? What sort of interpretability, etc. And then before deployment, just making sure we have a robust deployment, do some implementation testing, and finally, have the monitoring piece in place so that this is not something that is just let loose, but actually being monitored and being tracked in a robust way so that we can identify any changes and preempt those changes. And the last thing that spans across all these three steps in most of the industries that we deal with is regulatory compliance. We need to think about regulations in every part of the step and not just, once everything is ready. So any volunteers here as to in these three steps, how much percentage of the time, your team spends doing these three modeling, and model usage? Any volunteers here? Uh-huh. Yeah? Anyone else? So thanks to both of you. But I think like definitely, I in my experience, actually, free modeling is probably 50-60%. Model usage is the next biggest thing, maybe 20-30%. And then the modeling is actually the smallest component of the steps where a lot of times today we also have AutoML, which we can just plug in the data and, get the model. But we really need to think about the pre-modeling and the model usage steps, which would lead to a successful ML model. So starting off with business rationale. So this is like the first step even before you start coding, right? A lot of data scientists we might tend to start coding, right? Like, hey, we need to build this problem, but like in an industry setting, it's not Kaggle. We actually need to think about the business rationale as well. For example, to start with, does the model target variable actually align with the final business usage? This is a problem because otherwise we might end up building a model, but it might not align with the business usage, which would mean that the model is not going to be used, which is a waste of everybody's time. The next step is it going to be used for rank ordering or forecasting? And why this is important is knowing how it's going to be used should actually determine the metric for the model. How do we select the model? How do we choose the model and so on? And then another important consideration is latency. Is it going to be used real time? Is it going to be used in a batch mode? Because this would again put constraints on what model we actually go with. And the second last point here is, do we have to comply with any regulatory requirements? Again, very, very important. For example, in credit modeling, we need to think about ECOA, FCRA compliance, without which the model is never going to see the light of the day. And the last one is, how often will the model be retrained? We need to have a retrained strategy right before we start modeling. That would also help us understand and guide what kind of model we end up choosing. And I actually have a graphic of like a symphony here because I think at this stage, it's very important that we have stakeholder alignment, which would lead to the successful ML model deployment. We need to work across product, engineering, legal, the data science team, of course, and any other team that actually needs to be involved needs to come in right now to determine the scoping and the timing, of this ML deployment. Any thoughts here on the slide? So, like, I feel like this is definitely the gatekeeper for like machine learning models. And if we don't have a clear business rationale, like, I feel like this has to be rehashed, and we should not really be even thinking about building the model if we don't have a clear business rationale. With that being said, we can go to the fun part, that is the data part. First thing we need to start addressing is what is the data sources. If you're a mature organization, we probably have a neat data warehouse from where the data flows. But maybe some of the startups, we might actually have to build an ingestion pipeline. We need to make sure that the data that we're using continues to be available in the future. For example, if we scrape a website and then the website goes down, then that's not going to be helpful for the model. And then we need to think about if there's any upstream data changes, how it's going to affect this particular ML model. Because a lot of times our ML model is dependent on an upstream model. Like say, for example, a lot of our models might be using credit bureau data. What if the credit bureau data becomes unavailable? What are we going to do in that case? And then we need to think about data quality. And data quality is again like a moving target where it's not a point in time like, hey, is it good quality today? But how are we going to ensure and track the data quality? And then the data selection. What is the data in scope? Are there any exclusions? And we also need to make sure that we set the limitations and expectations correct. For example, if a global company was to build a model in North America, you can't directly take that model and use it in Australia, for example. You need to have your checks and balances in place before you actually roll out the model to a data distribution that it hasn't been exposed to. And finally, we need to make sure that, if there is any seasonality, we address it. For example, if it's a spending model, we need to make sure that it sees the holiday season, else it's not going to be robust for all periods of the year. And lastly, we need to make sure that whatever data we have a good appropriate sampling so that we can split it across, train, valid, and test, so we can actually start building the model. Continuing on the data theme. Once we have the data sources identified, what kind of data quality we have extra, we also need to think about data preparation, because this is where we need to start thinking about a little bit about what kind of model we are going to be using, because different models require different kind of model data transformations, and data preparation is also a time-consuming task, as you may all know. So we have, I chose a cooking and cutting vegetable thing here because this is where we tend to like slice and dice the data and chop it up, etc., and actually make sure that the data is consumable by the ML model. And then next we go to the variable selection, where we need to make sure if the variables we are using, do they cater to the business need? Do they actually make business sense? Because otherwise, especially when we're using complicated models, there tends to be a strategy of throwing the kitchen sink at a model, which may or may not be efficient. And then we need to think about, for example, categorical variable encoding. If you're using like non-numeric data, we need to make sure that we have an encoding strategy in place so that this would be, again, consumable by the model. And lastly, again, important even in the data step, is to make sure whatever data we're using, whatever features we're using, is actually compliant with any regulations that this model is going to adhere to. So now, I mean, like in my view, we have completed the tough part. For example, getting the business alignment, getting the rational set, etc. And we have the data, we have the modeling data, and like this is when I would say like 50-60% of the job is done. And then the next part is actually the modeling part, where we need to do the model fitting. For example, we need to choose the right algorithm. My recommendation is always to start off with something simple and then try out complicated models, because if a simple model can get the job done, we need to go in that direction rather than always choosing the more complicated model, of course, given the performance gaps. Then the next key, very important thing is the metric. We need to make sure that if you're using a risk model, then we need to make sure that the metric that we're using actually corresponds to the way the model is actually going to be used in the future. And then the next thing is hyperparameter tuning, which again, there are multiple ways of doing hyperparameter tuning, and these are decisions that every data scientist has to make. What kind of hyperparameter tuning are we going to do? Is it going to be a Bayesian search, a grid search, etc.? And then finally, we need to also, at this step, very importantly, make sure that if the model is over or under parameterized, and both of them are not ideal, because if it is, for example, over parameterized, then there's opportunity to make it simple. Whereas if it's under parameterized, that means that we are not capturing all the signal in the data, which is again not ideal. The next thing that we need to think about is actually analyzing the model. For example, a lot of stakeholders that we deal with today may not be very familiar with machine learning. How do we drive that trust within our stakeholders to actually make sure that they are confident in actually being champions for the model that we are building? This is how we need to actually go under the hood of the model and actually analyze the performance, do some scenario analysis, etc., to actually see how the model is performing under different scenarios. For example, we need to make sure that why are we getting these performance gains, what kind of features are we using, etc. And then we also need to make sure that if there's an existing model of strategy, we actually need to show the benefits of the model, right? Like this model is X percentage better than the existing model of strategy. And then finally, I think the other important part in this place is sometimes we might tend to use vendor models, which actually need to be evaluated in accurately so that we make sure there are no risks posed by vendor models, which tend to be a little bit more opaque than inbuilt model. So, and then the final step is actually the model usage, where we have a model ready, we have a model object ready, etc. And this is where we need to think about model interpretability. For example, we need to make sure if the top variables actually make business sense. And then the next one is local explainability. In a lot of cases, especially there are regulatory constraints in certain models, where we need to make sure we actually give the reason why we take a particular decision. This is why we need to make sure that the model actually is local. We have local explainability for the model that we have built. And then the next thing that we need to make sure is we need to make sure there's no disparate impact exhibited by the model. And my personal view is even though there might not be a regulatory need to do it, it might still be a good practice to do it just to make sure that this model does not behave in ways which we don't intend it to behave. And then again, the last piece is the regulatory part. And the next important piece is actually the model deployment monitoring, where we need to make sure that we do some implementation testing with the production environment. We need to make sure that the implementation testing framework is ready and the results that we see are actually satisfactory. And then we need to also set the frequency of monitoring. Is it going to be daily? Is it going to be monthly? Or is it like, hey, we're just going to be using this model till it actually blows up? And then we also need to make sure that we monitor the right metrics. Again, we need to monitor a few primary metrics and a few guardrail metrics. For example, it could be latency, it could be performance, etc. And then the next one is actually on data drift. We need to make sure that we have a plan in place to identify data drift. And data drift is especially could be risky because, for example, if the data that we expose the model to in production actually starts shifting, then it's going to impact the model performance a lot, and the model could again, experience a severe drop in performance. And the next one is also to set up a recalibration plan, which means that, hey, if we have like an X percentage drop in our particular metric, we are going to, do a data refresh, a model refresh, etc. So I'm just going to pause here for 30 seconds if anyone has any questions. Yeah. So I think the first step is like at least to acknowledge the problem. I mean, like even to analyze that it has the bias. I think second thing I've seen some people where they actually treat the data to de-bias the data so that the model is doesn't has that particular bias exhibited. And then there's this other thing that there are a lot of folks that tend to think that if a particular variable is not used, for example, if the model does not see the gender variable as such, then there won't be a gender bias. But I think that is also not the case because then there could be proxy variables which actually proxy for gender, which could actually end up biasing the model. And I think this is also like a tricky topic in the sense it's hard to address. First of all, we need to definitely acknowledge the magnitude of the problem because it's not something that's very easy to do. But I think definitely being more cognizant of the fact that there could be multiple biases that could be a part of the model. And I think there's definitely some regulatory constraints which we need to deal with, which would ensure that we actually check for these biases. But I think there is one strategy of actually debiasing the data before we feed the model so that the model is at least correct for the bias that it has been seeing in the data, which could be driven by, for example, say people's biases, right? So a lot of the historical data we see is actually induced by people bias. So that's another type of bias we actually need to overcome if we need a debias model. The modeling data. Yeah. Right. Yeah. Uh, the I mean, So I was reading a little bit about the Apple Card, the way they did the bias, and they basically claimed that I mean it was Goldman Sachs who actually I think built the model for underwriting it, and I think they basically claimed that they were not using that particular variable in the model because of which and I think they also got it audited by a third party which to say that there's no bias. So that's kind of what they did, but yeah, I'm not exactly sure about the mechanics of how that happened. So yeah. And then I would like to wrap up by talking a little bit about key principles. I think one of which was actually touched upon by one of you. So, yeah, definitely the first one is garbage in, garbage out. We need to be really careful about the data that we're actually using to build the model because if we are not exposing it to the right data, then we can't really expect right outcomes from the model. So we need to always double check the data integrity before we actually start modeling. Time spent on actually the data part is probably the most meaningful for a model success. The next one is bias variance trade-off. Bias is basically what is the error on the data set. Again, lower bias is better. And variance is how much does the model performance differ from data set to data set or under different scenarios in simple words. And of course, in an ideal scenario, we want low bias, low variance, but that's always not going to be the case. So we need to see how we can make this optimal trade-off. And then the last but not the least, one of my favorite principles that I always try to implement where I go is basically Occam's razor, which basically means try to use as simple a tool for a particular problem, or at least start off from a simple solution to a problem rather than directly jumping into the latest and greatest complicated architecture for a problem. Because a lot of times, I'm sure a lot of us would have experienced it ourselves, is even a complicated business problem could be solved by a couple of business rules, at least to start with. And we should definitely start off with something simple because it's more interpretable, it's more easy to deploy, it's more easy to communicate to our stakeholders and clients, for example. So definitely, I think this is another principle which is definitely going to help when we are trying to build complicated machine learning models, especially. Um, and for example, we should always verify if the final model can be simplified without any significant loss in performance. And on the right side here, I actually have a graphic of a Rube Goldberg machine, which basically, for example, Rube Goldberg was very famous for building these complicated machines to solve a simple task. For example, just to feed, you could build such a complicated machine, but this is probably not the ideal and most simple way to actually do this. So uh, that's all, and thanks everyone for attending. Any questions? We have like a couple of minutes left.